Let's jump right in. Welcome to today's Explainer. We're tackling something absolutely crucial today, the foundation-level data structures in computer science. You can think of these as the literal architectural blueprints that hold our entire digital world together. Seriously, whether you're building a tiny side project app or the next massive global social network, the whole shebang starts right here.
So here's the big question. How exactly do computers organize millions of data points instantly? Think about our physical world for a second. If you just toss all your tools into one giant, messy box, finding a specific screwdriver is going to be a total nightmare, right? Well, the digital world works the exact same way. Without a real, physical organization strategy for all that data, our computers would just grind to a complete halt trying to find anything.
Which brings us to the core of what we're talking about today, a data structure. What is it? It's really just a way of organizing and storing data so that it can be accessed and modified efficiently. It's exactly like how you'd organize books chronologically on a shelf, or systematically arrange clothes in your closet so you can actually get ready fast in the morning. Computers are the same. They need different organizational blueprints depending on the specific problem they're trying to solve.
To give us a mental roadmap for this explainer, we're going to group the 11 most important data structures into 4 main families. 1. The linear foundations. 2. The hash powerhouses. 3. The hierarchical trees. And 4. The complex networks. Let's get to it.
Starting off with part 1, the linear foundations. This is all about sequences and order.
Okay, the absolute most common blueprint you're going to see here is the array. It stores elements of the same type in continuous memory blocks. Best way to picture this, think of a large apartment building. Every single apartment has a sequential house number. If you know that number, which in programming we call an index, you can go straight to that specific apartment instantly, no wandering around. This gives arrays incredibly fast access speeds. But there's a catch. They have a fixed size. If the building is full, it's full. And inserting a new apartment right in the middle, oh man, that is extremely expensive and time-consuming because you basically have to shift everyone's furniture over to make room.
Building right on top of that concept, we have the string. A string is, well, quite simply an array of characters. Say you have the word hello. Internally, the computer is storing that as HELLO completely in order, with each individual letter getting its own index. Strings are totally your go-to blueprint for handling text, validating passwords, really processing any kind of written document.
And because strings are really just these organized arrays of characters, we can manipulate text at lightning speed. I'm talking accessing individual letters, concatenating, which is just a fancy word for joining two strings together, pulling out substrings, searching for exact patterns, or even flipping the text completely in reverse.
Now you might be wondering, what if we want that nice order of an array, but we need it to grow dynamically so we avoid those crazy expensive shifting costs? Enter the linked list. Here, elements, which we call nodes, are actually not stored in continuous memory. Instead, imagine a treasure hunt. Every clue you find contains a little piece of data, plus the exact address pointing you to where the next clue is hidden. This dynamic sizing is a real game changer, because inserting or deleting data is a breeze. The trade-off, though, you can't just skip straight to the end. You literally have to walk the path, node by node, clue by clue, to find what you're looking for.
Rounding out our linear structures, we have 2 blueprints that operate on completely opposite rules. First up is the stack. It's strictly last in, first out. Picture a stack of plates at a buffet. The last plate someone put on top is the very first one you pull off, hopefully without knocking the whole thing over. This is perfect for things like the undo button on your keyboard or tracking your browser history. On the flip side, we have the queue. This is first in, first out. Think of waiting in line at a coffee shop or a ticket counter. The first person in line gets served first. Computers use queues all the time for things like scheduling CPU tasks or sending a batch of documents to a printer.
Moving on to part 2, the hash powerhouses. This is where we get into instant lookups.
So, if linear structures are all about order and sequence, hash maps are entirely about blistering, unbelievable speed. I mean it. A hash lookup often happens in mere fractions of a millisecond. They completely bypass the need for step-by-step searching. Instead of scanning through a massive list to find someone's age, a hash map uses a key and value pair. It's like mapping the name Niranjan directly to the age 21. A mathematical formula called a hash function calculates exactly where that data lives instantly. This gives you ultra-fast searching, insertion, and deletion. It's absolutely the backbone of modern database indexing and caching.
And the closely related cousin to the hash map is the hash set. Imagine you feed your computer a massive list that has a bunch of duplicate 10s and 20s in it. A hash set instantly ignores all those duplicates and stores only the unique values. So, whenever you need to clean up repeat data or instantly verify if something belongs in a group, this is absolutely your blueprint.
All right, part 3, the hierarchical trees. Let's look at branching paths. A tree data structure is exactly what it sounds like, but upside down. It starts at the very top with one single root node, which then branches downward into child nodes, and keeps branching down until you finally hit the leaves, which are just nodes with no children. This hierarchical setup is exactly how your computer's file system is organized, and it's how corporate org charts are modeled too.
Now, a heap is just a highly specialized type of tree, and it's used specifically for managing priorities. In a min heap, the absolute smallest element is always kept right at the root so it can be grabbed instantly. In a max heap, you guessed it, the largest element sits right at the root. When your computer needs to quickly schedule urgent tasks or rapidly pull the largest or smallest element out of a massive dataset, it builds a heap.
And then we have the tree, that's spelled T-R-I-E. This is a tree custom designed for strings. Instead of storing the words cat, car, and can as three completely separate independent words, a trie stores their common prefix, CA, just once. Then it branches off into the different endings, T, R, and N. This shared prefix trick, that is the hidden magic behind your smartphone's autocomplete feature and the spell checker on your laptop. It's brilliant.
Finally, part 4, the complex networks, focusing on relational data.
The graph is really the ultimate relational data structure. It's made up of vertices, which are your objects or nodes, and edges, which are the lines connecting them. And those edges can be directed, undirected, or even weighted with different values like distance or cost. When you open up Google Maps to find the absolute shortest route between two cities, or when a social network suggests a friend of a friend that you might know, you are witnessing the immense power of graph data structures at work. It's how everything connects.
Okay, we've covered 11 distinct blueprints in this explainer, but here is the absolute core philosophy I want you to take away. You shouldn't just be memorizing these definitions. You need to understand when and why to use each one. Think of them as a highly adaptable toolkit. You need super fast lookups? Grab a hash structure. Need dynamic text search? Go build a trie. Once you really grasp these foundations, tackling complex coding challenges becomes incredibly intuitive.